Welcome to AI Frontiers, where we explore cutting-edge research at the intersection of artificial intelligence and scientific domains. Today's episode focuses on emerging trends in AI-driven software engineering, examining 19 papers published on May 7, 2025. These papers collectively illustrate how artificial intelligence is transforming software development practices, methodologies, and outcomes. We'll identify major research themes, analyze groundbreaking findings, examine common methodologies, and take a deeper look at three particularly influential papers that exemplify the current state of software engineering research. Software engineering focuses on the systematic design, development, operation, and maintenance of software systems. It encompasses activities ranging from requirements analysis and design to programming, testing, debugging, and ongoing maintenance. In our increasingly digital world, where software powers everything from smartphones to autonomous vehicles, robust software engineering practices have become more crucial than ever. The field currently stands at a significant inflection point, with artificial intelligence technologies being integrated into development workflows. Software engineering has evolved from structured programming and object-oriented design to agile methodologies and now AI-assisted development. What makes this particularly interesting is the growing tension between new technological possibilities offered by AI and the persistent engineering challenges of creating reliable, maintainable, and secure software systems. The first major research theme we observe is AI-assisted software development. Large language models are evolving beyond simple code completion tools to become sophisticated agent systems capable of complex reasoning. For example, Gao and colleagues present PR2, a system that uses LLMs to translate C code to safer Rust code by eliminating raw pointers, thereby enhancing memory safety. Similarly, Hu and colleagues introduce Compile Agent, an LLM-based framework dedicated to automating the compilation of large open-source projects, addressing the challenge of manual compilation, which becomes increasingly tedious and error-prone as projects grow in complexity. What's particularly notable about this theme is the shift from using AI as a simple code completion tool to employing it as part of sophisticated agent systems that can reason about code, understand errors, and take appropriate actions to resolve them. These systems are designed to augment developer capabilities rather than replace human programmers entirely. The second major research theme focuses on software ecosystem management and dependencies. Modern software rarely exists in isolation. Most projects rely on numerous dependencies and exist within larger ecosystems of related tools and libraries. Managing these relationships has become a critical aspect of software engineering, particularly as concerns about supply chain security have increased. Ganage and colleagues perform a comprehensive study of lock files across 7 popular package managers, highlighting how these files help ensure build reproducibility and dependency integrity, while also identifying challenges developers face when using them. In a related study, Ruhonen and colleagues trace how over 84,000 vulnerabilities have propagated across 28 open-source software ecosystems, revealing complex propagation sequences and lengthy delays that significantly impact software security. This research underscores the importance of understanding and managing the complex web of dependencies that modern software relies upon. The third major research theme encompasses both digital twins and code quality concerns. Digital twins, virtual representations of physical objects or processes, are emerging as an important research direction. Frasheri and colleagues demonstrate how the digital twin as a service platform can be extended to enable a federated approach to digital twin development and management. Meanwhile, technical debt, the concept that certain development shortcuts taken now will require additional work later, remains a persistent challenge in software development. Edbert and colleagues examine how scheduled deadlines impact technical debt accumulation in open-source projects, finding that deadline proximity can lead to increased commit frequency and bug-related issues in some projects. In a related study, Cynthia explores the identification and optimization of redundant code using large language models, addressing a common source of technical debt that makes systems harder to maintain and scale. These papers highlight the dual challenges of modeling complex physical systems and maintaining high-quality code bases. Several groundbreaking findings emerge from these papers that could shift paradigms in software engineering. Krinke and colleagues demonstrate that BigCloneBench, a widely used dataset for evaluating code clone detection tools, has been misused in ways that have harmed research. Through manual investigation, they found that 93% of weak Type 3, Type 4 clone pairs don't actually have similar functionality and are therefore mislabeled. This calls into question the validity of results from 139 papers that used this benchmark for semantic clone detection. Another striking finding comes from Guo and colleagues, whose OmniGIRL benchmark reveals that even the best-performing LLM, GPT-4o, resolved only 8.6% of real-world GitHub issues. Choung and colleagues present a comparative analysis showing that LLM-assisted code generation leads to a carbon footprint 32.72 times higher than manual development. Meanwhile, Gao and colleagues' PR2 system successfully eliminates 13.22% of local raw pointers in C to Rust translations, while Hugh and colleagues' compile agent improves compilation success rates by 10% to 71% compared to baseline methods. Researchers employ several common methodologies to address software engineering challenges. First, LLM-based agents combine large language models with specialized tools and strategies to perform complex tasks requiring both natural language understanding and domain-specific knowledge. For example, Compile Agent integrates 5 tools with a flow-based agent strategy to automate repository-level compilation. Second, empirical analysis of developer behavior and artifacts involves collecting and analyzing data from real-world software projects to identify patterns and challenges. Edbert and colleagues analyzed 12,300 commits and 371 releases across 8 open-source projects to understand how deadlines affect technical debt. Third, benchmark creation provides standardized evaluation of software engineering tools and techniques. Fourth, design fiction and participatory design methodologies explore future possibilities by engaging potential users in imagining and designing future technologies. Finally, mixed methods research combines quantitative and qualitative approaches to gain a more comprehensive understanding of software engineering phenomena. Let's examine our first seminal paper, PR2 Peephole Raw Pointer Rewriting with LLMs for Translating C to Safer Rust, by Gao and colleagues. This paper addresses a critical challenge in programming language translation, converting C code to Rust while preserving Rust's memory and thread safety guarantees. Existing tools like C2 Rust can translate C code to semantically equivalent Rust, but they rely heavily on unsafe constructs, particularly raw pointers, which undermines Rust's safety benefits. PR2 employs a novel peephole approach that uses large language models to lift raw pointers in individual functions to appropriate Rust data structures. The term peephole refers to the localized nature of the transformations, focusing on individual functions rather than attempting to transform the entire program at once. This granular approach makes the problem more tractable for LLMs. The authors implement a sophisticated decision tree-based prompting strategy to guide the pointer lifting process, breaking down the complex task into a series of smaller decisions. When evaluated on 28 real-world C projects, PR2 successfully eliminated 13.22% of local raw pointers, significantly enhancing the safety of the translated Rust code. The second seminal paper is How the Misuse of a Dataset Harmed Semantic Clone Detection by Krinke and colleagues. This paper challenges the validity of numerous previous studies in the field of semantic clone detection. Code clones, segments of code that are similar or identical, are common in software development, and detecting them is important for refactoring, bug fixing, and program comprehension. BigCloneBench has been a standard benchmark for evaluating clone detection tools since its introduction. The authors conducted a manual investigation of a statistically significant random sample of 406 weak Type 3, Type 4 clone pairs from this benchmark. Their findings are striking. 93% of these pairs do not have similar functionality and are therefore mislabeled. This high rate of mislabeling calls into question the validity of 139 papers that used BigCloneBench to evaluate semantic clone detection. Many of these papers report high F1 scores above 0.9, which the authors argue indicates overfitting to dataset-specific artifacts rather than genuine semantic similarity detection. The authors emphasize that BigCloneBench remains valid for its intended purpose of evaluating syntactic clone detection, but its misuse for semantic clone detection has potentially harmed progress in this field. The third seminal paper is OmniGIRL, a multilingual and multimodal benchmark for GitHub issue resolution by Guo and colleagues. This paper introduces a novel benchmark designed to evaluate how well large language models can automatically resolve issues reported in software repositories. GitHub issues are central to tracking bugs, feature requests, and tasks in open source development, and automating their resolution could significantly enhance developer productivity. OmniGIRL addresses limitations in existing benchmarks by providing a comprehensive evaluation framework that is multilingual, multimodal, and multi-domain. It includes 959 task instances collected from repositories across 4 programming languages: Python, JavaScript, TypeScript, and Java, and 8 different domains. The author's evaluation reveals a significant gap between current LLM capabilities and the complexity of real-world issue resolution. The best-performing model, GPT-4o, resolves only 8.6% of the issues in the benchmark. This performance drops even further for issues that require understanding images, with the best model resolving only 10.5% of such issues. This highlights the substantial challenges that remain in applying AI to complex contextual software maintenance tasks. Based on these papers, several promising future directions emerge for software engineering research. First, developing more sophisticated LLM-based agents that combine multiple AI techniques could address current limitations. These might integrate program analysis tools, formal verification methods, or specialized neural networks for code understanding alongside LLMs. Second, creating more rigorous evaluation methodologies and benchmarks that better represent real-world tasks will be crucial for measuring genuine progress. Third, exploring human-AI collaboration models that augment rather than replace developers acknowledges that fully automated approaches may not be feasible for many complex tasks in the near future. Fourth, integrating ethical and environmental considerations into development practices addresses growing concerns about the carbon footprint of AI-assisted development and the ethical implications of increasingly autonomous software systems. Finally, developing new approaches to managing technical debt in AI-assisted development will be essential as these tools become more widespread. By pursuing these directions, researchers can address current limitations while leveraging AI's potential to transform software engineering. It's worth noting that this presentation itself represents an interesting case study in AI synthesis and review. The content was synthesized using Claude 3.7 Sonnet from Anthropic, with text-to-speech generated using OpenAI's TTS technology. Visual elements were created with OpenAI's image generation capabilities. Human expert review was conducted to ensure accuracy and clarity throughout the presentation. While the content has been thoroughly reviewed, it's important to acknowledge that some oversights may exist in the synthesized material. This meta-level observation highlights both the potential and limitations of AI in synthesizing and communicating complex research findings, precisely the kind of human-AI collaboration that many of the papers we've discussed suggest will be the most productive path forward. If you found today's exploration of AI-driven software engineering valuable, consider subscribing to AI Frontiers for weekly research syntheses. Our community brings together AI and technology enthusiasts interested in staying at the cutting edge of research developments. We encourage you to share your thoughts in the comments section and suggest research areas for future episodes. Visit our website for extended analyses and additional resources that dive deeper into the topics we cover. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.